So the next speaker would be Michael Everett from Google. So maybe when I'm introducing speaker, maybe Michael could start sharing the screen. So our next speaker is Michael Everett. Michael Everett is currently a visiting faculty researcher with Google's People AI research team, and he will joining Northwestern University in January 2023 as an assistant professor, and with a joint appointment in the Department of Electrical Computer Engineering and the Khoury College of Computer Science. His research lies at the intersection of robotics, deep learning, and control theory, with the goal of developing certifiable learning machines. Previously, he was a research scientist and a postdoctoral associate at the MIT Department of Aeronautics and Astronautics, working on the DARPA RACER program, and advancing in the field of certificate learning. He received his PhD, Master in Science and Bachelor in Science degrees from MIT in Mechanical Engineering. The stage is yours, Michael.
Cool. Thank you for the introduction, and thanks to all the organizers for putting together a great workshop on a really important topic that's near and dear to my heart. So I'm going to be talking today about what I call certifiable learning machines, and it's really going to be thinking about how we can provide some formal guarantees to the exciting AI models that are coming out of all sorts of different fields, especially when they're deployed in real environments right alongside people. So without diving in too far, I want to just acknowledge all the folks that I've collaborated with on the work today. So Nick Rober, Gulnaz Habibi, Chuang Sun, and my advisor from my PhD, Jonathan Howe. And a lot of this work was done funded by the Forward MIT Alliance. So one of the, I think most succinct ways to describe what I am really trying to accomplish with one of my threads of research is, you can imagine, as a grad student, you just finished training your neural network on some AWS system last night. You're really excited, and then you need to convince somebody that you're allowed to run that new policy on their $1 million robot. Or if $1 million doesn't get you excited, maybe $1 billion vehicle that's going to space. So that's sort of a big question that we don't really have the techniques to sort of address yet. And so there's definitely technical things we need to develop and sort of tools, as well as conveying those to people that are not as technically experts in this area. So finding ways to communicate these types of guarantees to the public as well and other stakeholders is sort of a big motivation for a lot of this work. So kind of some of the motivating examples I have pictured on this slide are, thinking about this type of off-road vehicle where, a policy all of a sudden it's very important if it's safe or not, because people's safety is kind of directly at play, as well as if you're going to maybe deploy some sort of underwater robot in a mission that happens once a year or once every few years, and you want to make sure to justify that your new algorithm should really be getting that valuable time on the platform, and the platform's not going to drift off to some place and be unrecoverable. So, the types of tools that I'm trying to develop are thinking about, neural network controlled systems and their safety, stability, and robustness properties with respect to noise and uncertainty in the environment. So to be a little bit more concrete about what I mean, I'm going to describe over the next several slides about how we can actually analyze neural networks. And in particular, we can start off by thinking about just analyzing neural networks in isolation. So without thinking about the complicated dynamical system they may eventually be controlling, just zoom in on a policy that's been trained already. So typically the way you'd use a trained policy is, you take some measurement of the state, maybe it's like x0, x1, and then you pass that through as inputs to your policy, and then you get some control actions, which will be implemented. That works just fine when you have perfect measurements of the state, and you'll get reasonable actions if it's been well trained. But let's say it's a little bit more of a realistic setting and you don't actually know exactly what your system's state is. So you have some uncertainty about your state in the state space. What this actually looks like now is more like this picture, where now maybe you have some uncertainty on one of your state dimensions, x0, and some different amount of uncertainty on a different state dimension. And that nominal measurement is just kind of one point in this set. So the question is, how can we be sure that, regardless of where we are in this set, the outputs that our policy is going to put out are actually also reasonable and not going to violate some constraints? And this problem is really difficult to kind of think about exactly, because mapping this type of set through a super nonlinear high dimensional neural network leads to this NP-hard problem to compute this sort of green mapping of this green set exactly. So while it's really difficult to do this exactly, we can do the next best thing, which is to over approximate or bound the set of possible neural network outputs. And that's depicted by this blue set right here. So if we can make a guarantee that the abstracted or over approximated system is not going to violate some constraints, those guarantees also hold for the exact system that was difficult to analyze perfectly. Okay, so how do you actually do this sort of analysis, and how do you make these approximations? Well, the key ingredient that a lot of the literature has taken and run with so far is that for each nonlinearity in your network, that's really where a lot of the difficulty lies for the analysis. We know that if, say, the input layer has some bounds, exactly sort of the input range of your sensor measurements, then each of those nonlinearities also has a bound on its inputs, and that means it also has a bound on its outputs. And so some different of these bounds can be depicted kind of on this continuum of being really fast to compute, but a little bit coarse. So say a ReLU, if the input range is within some range Z, maybe the output is within some interval bounds depicted by these red dotted lines, or you can go a little bit more accurately and kind of use linear bounds or quadratic or sector bounds, or even kind of write the whole thing as a mixed integer linear program. And so there's kind of this trade-off here of trying to understand, can I quickly analyze these systems and sacrifice a little bit in terms of accuracy, or do I want to solve the full problem exactly and potentially spend a really long time doing the analysis? So if you have all year to run your analysis, it doesn't really matter how long it takes if you're just going to do this once. But one of the things that really motivates pushing towards this left end of the spectrum is if we want to do this type of analysis during training to make our policies more aware and actually respect safety guarantees as part of the training. Because then you could imagine you're running these analyses, millions or billions of times, and each time you do it, you suffer a little penalty. Okay, so that's sort of kind of the key ingredients of thinking about relaxing nonlinearities as how we can analyze neural networks. Now I want to talk a little bit about how we can analyze neural networks when they're embedded in feedback loops. So I like to call these neural feedback loops. And so that's a very common way or kind of a picture for describing how we typically implement control policies. So maybe this neural network's been trained for your planning or control modules. It's passing control signals off to your system, which is moving through the environment, sensing the environment. And then maybe those sensor measurements are going to some perception module, which maybe is a separate neural network, or maybe these are kind of all one bigger neural network, depending on your architecture. But in general, thinking about that, the fact that now your neural network's outputs actually impact its future inputs, that's kind of the key challenge that as we think about safety of these control policies and feedback loops. And of course, uncertainty creeps into this problem all over the place. So we may not know exactly where our system is starting. There's this nonlinearities that we have to deal with. There's process noise, sensor noise, and all sorts of other things can happen throughout this feedback loop that we really want to be robust against and have formal guarantees for. So the kind of tool set that I've been developing can be captured as this concept of reachability analysis. And that's something that's been around for a while, but we're bringing it into this neural feedback loop setting. So I can be a little bit more concrete about what I mean with reachability analysis. Sort of a cartoon form of reachability analysis in forward reachability analysis is, say your system, I have it pictured as a little drone. It has some neural network control policy that's already been trained, and you're given some initial state set, this golden rectangle, which is all the states that your system could start from. If you were to just basically press play and run the system forward a bunch of times from different initializations in the set or different realizations of the noise in the environment, then you'd get different trajectories running forward as the system tries to be controlled towards its goal set. And so rather than just running a bunch of the Monte Carlo simulations, which is one way to get a sense of what the system might do, that's always going to give you an under approximation of what your real realizations of the trajectories could be. So we're going to come from the other direction and try and come up with over approximations that are guaranteed to bound the set of all the possible realizations. And that's what all these little green rectangles represent, as all the reachable sets, or all the sets of all the states which your system could reach at each time step in the future. And to tie that concretely back to safety, if you wanted to make sort of a stamp of approval and say your system is verified to be safe, you could just check that these reachable sets don't intersect with your void set and make sure like the last one ends up in your goal set. And those are really simple operations once you have these sets computed, but actually computing the sets is the challenging part. Okay, so all of the things I just said are written over on the left of the slide in equation form. So, start with some initial state set, which happens to be equivalent to your initial reachable set. And then each next reachable set is just passing that previous reachable set through your dynamics F according to your control policy pi. And one of the key assumptions that we're going to make here is that we actually know the dynamics of our system ahead of time. So somebody tells you the A, B, and C matrices, just so that it kind of describes how your system evolves over time. But the nonlinearities come in the control policy, and there's some bounded noise that we know the bounds of, but we don't know the exact realizations of. So altogether, this dynamical system will be nonlinear because of the neural network. But to make the analysis easier, we're going to assume we have some linear dynamics to start. Some of our more recent work has relaxed this need to have linear dynamics, and we can also handle non-linear dynamics with some other techniques as well. Okay, so in terms of sort of the technical approach, we're going to compute these reachable sets sort of in 3 steps. And we're going to do this recursively. At each time step, we're going to compute the next time step's reachable set. So let's say we first want to just do the neural network relaxation that I was talking about a few slides ago. So just looking at the neural network itself, we know that our system is starting within some range of states X in, and we know that our policy pi could be some like super funky nonlinear, it's a neural network after all. It could be some nonlinear function of the inputs. So what we're going to do is we're going to relax that function and get these affine bounds, which are these dotted lines, and we'll call that pi u or pi l for the upper and lower versions of the policy. We can pass those upper and lower affine bounds, which are much easier to deal with in through our dynamics. And we can actually end up with sort of a upper and lower limit on our dynamics. So now this plot is, plotted on the x-axis in terms of the state at time t versus the state at time t+1. And then we can do pretty simple linear programming to just find the extreme of these functions once they've been nicely relaxed. So all this analysis turns out to be like just a matter of solving linear programs, which can be done very efficiently and actually done in closed form for certain representations of the states, such as hyperrectangles, and that allows you to solve these things really efficiently online. So if you're interested in trying this out, I would encourage you to take a look at our GitHub page. So I have the URL listed right here, but it's sort of this neural network robustness analysis repository. And for the feedback loop verification, I'll kind of describe sort of how you might use it right here really quickly. So you would, as a sort of person, interacting with the code, you would need to provide a few pieces of information. You'd have to give it your trained neural network. So give it like the model parameters and the weights. You'd have to give it a function of your dynamics. So we have a bunch of systems already implemented, but you could easily implement another one. And then you'd tell it what's your initial state set, and then choose which of the different variants of the algorithms you want to use, and it will compute these reachable sets often into the future from as many time steps as you'd like. And so that's visualized over on the right here as kind of an animation where this is for a pretty simple double integrator system, just to kind of show something that can be visualized easy. We sample a bunch of points from the initial state and sort of do the Monte Carlo strategy of just trying to see what will happen for specific realizations. And then these blue sets are being refined using our algorithms to actually compute pretty tight reachable set over approximations that are definitely always going to bound the Monte Carlo samples. So I didn't talk much about the sort of partitioning, but there's sort of this other whole set of things, tools we've developed for splitting these input sets into smaller pieces in an efficient way to make these kind of get refined more and more efficiently. All right, so I want to spend some time talking about the backward case as well. So I'll just quickly say that sort of in terms of runtime, these things are super efficient. So like 0.01 seconds to solve this type of problem with some of our recent algorithms. And there's sort of like big amounts of reduction of error with way faster calculations than what was done before. But the key thing is these are techniques so that we can verify that a system actually achieves its task, even though the fact that there is a neural network in the feedback loop. We can scale these things up to pretty reasonably sized systems. So here's a 60 quad rotor. This can be computed pretty quickly using the exact same techniques I talked about before. This is actually a 270 state model of a component of the International Space Station, which I thought was pretty sweet that I found some link in the model reduction literature and tried it out, and we're able to compute bounds on all 270 states. Here I've just shown the first two so that our heads don't explode trying to think about that many states. And then here's a Duffing oscillator example. I alluded to the fact that we can do this with nonlinear systems as well. So a simple nonlinear systems, we can also compute these bounds. Okay, so I just mentioned that I want to talk about backward reachability analysis. And this is some follow-on work that Nick Rober has been leading at MIT. And this is, to me, I think a really cool way to bring this reachability analysis problem into another sort of practical instance where we have a collision or an obstacle in the environment that we'd like to guarantee that our neural network is not going to drive us into. So what's sort of the issue here? If you imagine you have some robot, it's got some trained policy just like before, and there's an obstacle in the environment, so it's trained so that it knows to avoid the obstacle and go to the if you have this pretty common property of these systems where it might actually avoid collision by passing on one side or another, depending on where it starts in the state space, that's going to present some pretty big problems for our forward reachability analysis, particularly if we use these convex reachable sets, because these reachable sets are now going to have to span both possible options of the trajectories that are, what we say bifurcating around this obstacle. So all of a sudden now we can't actually guarantee that systems can be safe because this reachable set intersects with our obstacle, even though it's kind of like, oh man, I wish we could just subtract out this region because really we have these kind of two distinct disjoint reachable sets. But the forward techniques that we've developed so far don't really allow us to do that. So we were trying to think about how we can do this in another way. So instead we decided, let's try and think about this in reverse and think about, given that you have some, say, obstacle set, let's try and think about all the states that could drive you into that obstacle set according to your control policy. So remember before we were thinking about starting from an initial state set, where are you going to move in the future? Now we're thinking about starting from a thing you want to avoid. How do you make sure you don't end up going into it? And this is a very common way to formulate the problem in classical control theory of thinking about forward or backward reachability analysis. And typically it's very easy to switch between the two, except in this case, when we have neural networks involved, thinking about inverting a neural network, that's sort of a big challenge as well. So just to give you like one example of why, think about inverting a ReLU. If you knew sort of your control values lie within some range, all of a sudden, like you can't really bound the set of possible things that would have led you to make that decision. So that's sort of one problem. And then the matrices are not necessarily invertible or could be rank deficient. So lots of problems could come up with inverting neural networks. So let's try and just avoid that altogether. Let's try and keep leveraging the tools we've developed so far for analysis in the forward direction, but still bring those tools into the backward direction. Okay, so I'm going to give like the quick version of this story about how we do the backward reachability. I'm happy to talk more if there's time and sort of the details, but what we're going to do is we're going to take 3 steps. Okay, the first is we're going to try and think about what are all the possible previous states that we could have come from, given that we know some set of states that we are trying to reach or given as kind of the obstacle set. And let's ignore the neural network first, and let's just think about, given that our control policy just has some limits on it, like to make sure we don't violate the motor saturation values. And let's just think about all the states that could kind of get us into the obstacle subject to those control limits. And that'll be called the back reachable set. Then we're going to relax our neural network over the back reachable set in those techniques I presented at the beginning of the talk. And that's going to give us this nice relaxation of our controller. And now we don't have the like super nonlinear thing to worry about. We have these nice, easy to deal with bounds. Then we can write some linear programs where we try and find all the previous states that lead us into the target set, given those affine control bounds, and we'll call that the back projection set. Okay, so there's sort of this distinction between back reachable and back projection set, and we go through sort of formal definitions of these in the paper. But to give a sort of illustration of what's going on here, this is for a simulation of a little 2D simulation of a mobile robot, ground robot. And just to show that sort of forward analysis, we trained a policy with some like simple obstacle avoidance algorithm, just trying to avoid this obstacle. And that works in the forward case if you have sort of an offset between where your initial state starts and where the obstacle is located. But if you just move this initial state set down a little bit, the forward analysis technique, all of a sudden those rectangles that I said were going to get super conservative, those same blue rectangles are now huge and getting like ridiculously unusable. So the backward techniques, fortunately, they actually solve this problem where now we're starting from our avoid set and we're just computing these blue rectangles, which are all the states that could lead us into that target set. And we just have to check, oh, there's no intersection between our initial set and our computed back projection sets. Perfect, we can guarantee safety of our system. And we just show for completeness that we have some Monte Carlo samples of our policy, and those happen to avoid the obstacle as well. So that's just kind of a sanity check. Nick has recently extended this idea up to this quadrotor model. So before I was showing sort of simple 2D mobile robots, here we have a 6-dimensional quadrotor, and sort of the key ideas of trying to do this analysis in higher dimensions are new techniques for eliminating some of the unnecessary linear programs that are being solved, as well as new techniques for partitioning these sets to tighten the estimates in a more intelligent way. So here, same kind of takeaway as before. There's no overlap between these blue sets, which are all the states that could lead us into the obstacle. And that allows us to just check no overlap between those blue sets and our initial set, put your stamp of approval on, and your system is certified to be safe. So I've got a couple more slides that are sort of going through the sort of details, but all in the interest of time, just kind of wrap up and leave time for questions. But I want to make sure I get a chance to mention that I'm going to be starting my group in January at Northeastern University. I'd be super interested if folks are excited about these topics. If you're interested in doing a PhD, if you're not already, feel free to apply to our program. And I talked a lot about safety today, but other topics that are of interest are RL in general, model predictive control, social navigation. So picture from some of my work earlier on is shown up here, trying to deploy these systems in real life alongside people, as well as pushing the limits of how fast these algorithms can run in autonomous systems. So with that, I'll just wrap up. I'll open up to questions, and thank everybody for their time.
Thank you, Michael. Thank you, Michael, for the wonderful talk. Let's see what the audience have for questions. If you have questions, please ask that in the QA section, or you can raise your hand. So to promote you to be a speaker.
Meanwhile, I have a question. So thank you, Michael, for the nice presentation. My question is about the general topic and applicability of the reachability analysis if we don't have the dynamics of the system in an analytic form. And for example, considering the model-based RL methods that we are trying to learn the model of the system by a neural network itself, and beside the policy that is neural network based. So how the analysis and this reachability things can for the safety aspects can be extended to those questions?
Yeah, thanks for the question. So thinking about how do we extend these techniques to systems where we actually don't know the dynamics ahead of time? Yeah, so that's something I'm really interested in. We're sort of working on it as well in parallel. So there's sort of two ways to think about this. One you mentioned is learning your dynamics as another neural network. And another way is maybe you could learn it in some other parameterized way with some maybe uncertainty bounds. And that's pretty common in like adaptive or robust control literature, is thinking about maybe I don't know my, say, mass parameter of my robot, but I can sort of estimate it from data online. I think the key ingredient to be able to close that gap is we need to make sure that the dynamics models we're learning are also guaranteed to hold. So either we need to know them, perfectly, or we need to know them with guaranteed uncertainty bounds, because then we can sort of just plug that in as a slightly more conservative, for instance, version of the dynamics model we're already using. So there's definitely ways to work that into the system. I think the hardest part is learning the model of your system in a way that you can certify as well.
Okay, and the connection to have the uncertainties in a form that can be used with this analysis tool. So like if there is a probabilistic uncertainty of the neural network model, how can we form it into the framework that for the reachability analysis is trying to use these uncertainties as the like process uncertainty or the observation uncertainty or like these additive things?
Yeah, so I didn't talk at all today about probabilistic methods. These are all like formal methods in the sense that we'll get 100% guarantees, these things. I think you could probably have much tighter results with slightly lower probability of them holding if you want the probabilistic model direction. But I think the things that I'm really interested in are, could we learn a model of our dynamics with guaranteed bounds, not probabilistic ones, because then I think we can plug it directly into this framework.
Okay, sure. That answers my question. Thank you.
Cool.
Yeah, let's see whether there are other questions. I might have a question. So based on this analysis results, is that how could we leverage this to help the training for better agents, safer agents?
Right. So I talked today about just the analysis phase. So once it's been trained, we can give guarantees on it. But I think the question is, how can we bring that into the training process and have agents that actually learn to update their policies while also respecting these constraints? And that's another one that it's sort of ongoing work. I hope to publish it soon. So I'd say stay tuned for that. But I think there's a lot of cool ways to sort of make these techniques that I described today differentiable, and then we can directly embed them into the training process.
I look forward to that. Thank you. Oh, okay, I think so. There is another question in the Q section. Can this neural network verification results be used as constraints in optimization-based controller synthesis, like some safety certificates in controller?
Yeah, so I think that relates closely back to the previous question of, when you're thinking about doing the control synthesis, how do you leverage these analysis results? So yeah, I'll let the cat out of the bag that yes, we can use these in optimization as either losses or as constraints, and that's something that's definitely possible to do. It's just a matter of making the techniques efficient enough that you don't have to spend multiple seconds each time you're trying to do a gradient update or an epoch of your training process and slow the whole thing down. So yeah, there's definitely ways to leverage these techniques in training.
Okay, thank you, Michael. For the time's sake, I think we might close the talk here. And so for the questions, might direct to the chat channel or the Q section.